electromagnetic wave which will pass along this surface like this, right? So this is the wave. You see, this is like positive, negative, the electromagnetic field here generated already, and it moves in the on this surface. So it doesn't go in this direction. It doesn't go in this direction. So if you see this graph here, so when you go in this direction, in z direction, it decreases and vanishes, and same happens. It decreases and vanishes if you go into metal. So most of the field intensity is confined into this area. That means so that's what I was saying, that is squeezing light. So as in a matter of saying, we squeeze light on this interface by using surface plasmon method. That means if there is a point, something kept here, then we can see using this light. So we cannot see using the light that we incident upon like this, but we can see using surface plasmon. Well, yeah. So I hope that's, because this is a huge topic. This is the whole research field. So it's hard to tell you everything in one slide, but I just wanted to tell you the gist of surface plasmon idea of what happens. So, or to make it more clear, as I said, surface plasmons can only exist at the interface between a positive permittivity material, which is dielectric material, and a negative permittivity material, which is metal. So you need to have interface of metal and dielectric for that to give you this surface plasmon wave on moving on the surface. Now, since this is the electromagnetic wave and it can move forward, so if you have, let's say, metal film, well, it's hard to, it has also its limitation. So just agree with me at this point by saying, okay, there's a limitation, because this is, again, a very technical detail. It needs to be mentioned why it has limitation. But to tackle that limitation, what we do, we use, instead of a metal film or metal interface, a large film, we use particles or small spheres, or also known as nanospheres. So you can use 1 nanosphere, you can use 2 nanosphere together, and those sort of things. I'll tell you how, and I'll give you an example of that as well. So if you see this slide and the picture on the right here, what happens is you have a nanosphere here, and it is made of metals. In this case, it is, let's say, it's gold. So normally when you deal with plasmonics or surface plasmon or nanoplasmonics or nano-optics in plasmon, all these terms, if you think about, you deal with metals which are coinage metals. For example, like gold, silver, aluminum, and all these materials. So when I say gold material or silver materials, they are in nano regime, not in bulk. So bulk gold has very different property than nano gold, right? So this is very it's not that trivial, and it's very tricky to find out the nano gold properties. So when you have a nanosphere made of nano gold, and if you send a light, so this is a light, or electromagnetic wave, which has a wavelength certain lambda. If you send it, and these are electromagnetic oscillations, right? So this is oscillating, like going like this, oscillating, going up and down like this. So what happens? It also oscillates the electron inside this nanosphere. So that means the nucleus goes this way and the electrons go this way. Now there is a net electric field into this direction, and when it goes opposite, there is a net electric field into this direction. So this is the plasmon field, right? This is E plasmon. So now what's the beauty of nanosphere is, when you have a nanosphere and you have electric field confined onto the surface, it cannot move anywhere. It's already confined, but it's also confined into certain part like this. Sorry, like this part. So either here or here. So this confinement area is very small, and this area gives you a very better resolution compared to the diffraction limited optics resolution that I was talking about earlier. So that resolution, so if you think, so that was around 1.6 lambda n by Na. And this gives you, if you think about, let's say 500 nanometer of wavelength, this gives you about 250 nanometer resolution. That means if you have 2 points that you want to see together, if they are far apart than 250, then you can see it. If they are, let's say 100 nanometer apart, you're going to see it. But in this case, in nanosphere, if you have, if you squeeze light, so this distance is let's say 1 or 2 or 3 nanometer, 2 to 3 nanometer, something like that. So now you see that your effective resolution has decreased a lot. So if you shine light like this, yeah, from let's say from here, from below, and you have this area, and this area acting as a 2 points where the light is squeezed. So if a particle is attached here, 2 particles attached here, you can see it clearly using this metal nanoparticle. That's what I wanted to say. Now, so that's the gist, or that's the core property of surface plasmon using metal nanoparticles, and that's also known as localized surface plasmon resonance because it's very localized into nano dimension. Right. Yeah. So again, Asutosh, everything is going fine, right?
Yeah.
Okay. Great. So now let's move into giving you some examples. So when you do research, you have you publish your results and then you show. So just to tell people who are new to this, when yeah, to mention the process. So I took this picture from a research paper from Stephen Mayer here, you see. So you can go and check this out if you want to know about more. So Stephen Mayer is one of the pioneering scientists in the field of nano-optics as well. So I took this picture from his paper, right? So because it's a very good example for giving you an introductory idea about metal nanoparticles and how they behave. So this picture is taken from a microscope in a lab, right? Where you see all these circles are diffraction limited images of metal nanoparticles. This one, everything. But if you zoom in by using, let's say, there are other methods like a scanning electron microscope and TEM, transmission electron microscope, all these apparatus or techniques, then you can zoom in to see they have different structures. Like this one is triangle, these one are 2 spheres, this is a nanorod instead of nanosphere, then this one is triangle with a nanorod, things like that. Now they all have their different properties, and they all have different properties. That means different plasmonic properties, and they all get excited at a particular wavelength. So that means they can squeeze light at particular wavelength, which is plasmonic wavelength or plasmonic resonance wavelength. Right. So if you see this graph here, so the lower x-axis shows the energy, which also gives you the wavelength lambda. Right? If you can convert this electron volt energy into lambda. So you see this nanorod has particular energy where it can confine light, right? So if you connect this to this, so if you excite it with electron, so these colored areas are confined light areas, which is also known as hotspot. So I'll call it hotspot from now on, where the light is confined to give you better resolution. You see, and also, I mean, all these nanoparticles, let it be spheres or rods or triangles, they all have their own plasmonic resonance wavelength to So it's not like you can shine light with any wavelength and they give you confined light. No, they have a particular wavelength or particular energy they need so that you can get confinement of the light in the hotspot. And also it depends very much on the size and the size. That means what's the size of the nanoparticle. And on the, for example, this graph itself shows you that all these are nanorods with different size, and the wavelength changes every time the size changes, and the shape, for example, from rod to triangle and from triangle to sphere, it will change as well. So if you want to use particular wavelength, you can design your nanoparticle at that wavelength by doing simulations to find out which nanoparticle you want, and you can either fabricate it by different methods out there to see and or to use it in your experiment, or in your biological sensing measurement, for example, to have better resolution. Okay. Yeah. So I hope somehow understandable at this point. So yeah, so I'm going to give you an example from my research after this one, but I wanted to know if everything is okay. Asatosh, yeah?
Yeah.
Yeah, and also there's no questions so
No,
far.
no.
Yeah, so great. So let me move ahead. So now you know about the diffraction limit. Now you know that the light can be confined using metal nanoparticles. There's a surface plasmon wavelength, particular wavelength that you can need to use. All these things. So these are all terms. Of course, you cannot remember it forever. If you are interested, you can read about it. There's a plenty of textbooks and articles and papers out there to know about it. And as for example, if you're doing a diploma here, let's say in science, physics somehow, and so I hope that there are some people in the audience who are related to science, physics, or basic science. If they want to do, let's say, the research in optics or in nano-optics, then you can use this. You can use this opportunity of this talk to understand what's going on in plasmonics. And if it interests you, you can pursue a research in this field as well. Well, now, so let's say now before I tell you about the example from my work, I'll talk about again the diffraction limit, but in this case it's a confocal microscopy method. So I don't know if anyone of you have heard about confocal microscopy earlier. So it's just a method of seeing or detecting molecules in a microscope, but there are certain experimental setup that you need to provide to get better resolution that most of the biological experimentalists use. So this is very common confocal microscopy setup, or the term that is used by people all over the world since a long time. So what happens in this case, you have a microscope objective, and you shine light from below, let's say a laser light at certain wavelength, lambda. Of course, this is going to be, you have to tune this lambda or make this lambda. If you want to use a metal nanoparticle, you have to tune that. Great. So in this case, what you see here is when you shine light using this objective, and this is your sample stage, right? This is your sample, and you pour a solution on top of it. So this is a solution, let's say in water, and you pour, and in water you mix dye molecules. So these are fluorescent dyes, right? Fluorescence, right? So because I said earlier when I was talking about fluorescence, phosphorescence, that I'll talk about fluorescence more in coming slides. So this is the point where I'm talking about it right now. So here I'm telling you about fluorescent dyes. So there are many molecules which are called fluorescent dyes that gives you fluorescence. So you're excited with certain wavelength, and it gives you fluorescence at higher wavelength. So here is a solution with so many dyes molecules in it. And this blue area is the focus of the laser, or the diffraction limited area, as I was talking about, that if you focus a laser light or light, it will give you not the point, but an area like this one. So this is the same area. Now, what you see is when you want to see a dye molecule in this area, so there is not one, but there are plenty of it. And of course, you need to have better resolution to see, let's say one dye. If you want to see one dye molecule, you have to reduce this, right, a lot. So if you, for example, I'll draw it here. So if you have this much area, and from here, if you crudely, if you say you have like 4 molecules you can see, so this is like 2 or 300 nanometer size. And if you want to see this in this light, if you want to see one molecule, so all these dye molecules are what, around, let's say 5 nanometer or 10 nanometer, let's say even like 50 nanometer. So if you want, you cannot see more than 4 to 5 molecules in this. That means all these molecules will turn out to be one big circle. You cannot resolve 4 molecules. So what you need to do, you need to squeeze light or confine light so much that it can give you smaller effective like area here so that you can see one molecule, right? That's what we are planning to do. Well, I'm going to skip these couple of slides because these are just a matter of making it fancier, which I'm going to skip at this point. This is not going to remove or add anything at this context of the talk at this point. So just use. So from coming from the earlier slide to this slide, so as it looks similar, right? So there's the focal spot of the laser or the area where you want to see, and then you use 2 nanospheres, metal nanospheres made of gold together, similar, and the distance between these two is, let's say, 2 nanometer or something like that, 2 nanometer. And this is, let's say, the nanosphere is of the size of 50 nanometer, right? So this is in total, let's say 100 nanometer, and your this focus size is around 300 nanometer, right? So what happens, as I was telling you earlier, by the property of surface plasmon, if you excite it with a lambda wavelength, which is going to excite the plasmonic property of this 2 nanosphere, you'll see squeezing light in between this 2 nanometer, like hotspot I was saying. So now the effective area is going to be, instead of 300, is going to be, for example, it's very ambitious to say, but I'll say, let's say 2 nanometer, or not 2, but let's say 10 nanometer. But even that is enough, okay, because then you can see single dye molecule, which if it passes through this area, you can see it. And all these molecules you will not see, they will act as a background noise. And there is a method in optical experiments that you can remove this noise by using some sort of optical elements called filters. So what you will see, so what happens, all these signals, you record fluorescence signals as a fluctuation like this. So if you have like time scale, and this is intensity scale, like intensity of this light signal that you record. So you'll see signal like this, too much noise. So all these are acting like this. But let's say a single dye molecule goes into this area, then you see a jump in the signal, blah, blah, blah. So this corresponds to one dye molecule, which is here, right, which is in the hotspot. And then you keep recording, you'll see background, background, background. Then another molecule goes into that area. You see one jump of the signal. So because it is, you can actually see that, and it gives you higher because you have squeezed light into this, and you can see it clearly. Now, to give some experimental measures, I'll skip that too. I'll just give you a brief idea about the setup, sort of normal setup that you can use if you want to do in future, or if you are doing experiments, optical experiment in your lab, and you want to improve, or you want to get some idea, or you can tell me later that you are doing it wrong. You can. I'm open to suggestions as well. To say. So what happens? You have. So this is your setup. What happens? So the area that you are seeing is basically this microscope here. This is your eyepiece. You can see it through. or you can use a detector as well. So there are numerous types of detectors that you can record signal through. And this is your sample stage where you can keep your sample. And from below here, you can see you can send light up to the sample and collect it back in this setup and send it to your detectors like this one here, or APD detectors like this. So basically, so this is excitation part here. So this is a laser, helium neon laser using 633 nanometer wavelength. You send light, so there are a bunch of optics, you don't have to worry about it. Just send light using this path. You send it like this, goes ahead inside and excites your, let's say here is your sample. So here you'll see this type of, as I was talking in the earlier slide, you have your 2 nanospheres, your solution in your dye molecule, they pass through this hotspot, and then you collect the signal and you send it to your detector. This is a detector called avalanche photodiode detector. So that this is a very fancy and robust detector that can detect even signals in the resolution of nanosecond or picosecond like that. So yeah, that's just a brief introduction of the setup that you can use. So what happens is, as I was telling you about the example that I had done during several years of my research, that I used, let's say, a single sphere, or I used double sphere. So these two images are taken from scanning electron microscope. So these are where you can zoom in more and you use electrons to image your nanoparticles. So there's a single sphere, the size is in the range of 80 nanometer. If you see this scale bar, and these are nanodimers or 2 nanospheres called nanodimers. So this will give you this result. So what happens if you use a gold single nanoparticles? When I say detection volume down to this area, so this just a number that's showing that the volume is reduced, let's say 1,000 times, something like that. And also it can enhance the fluorescence signal 60-fold because of the confinement of hotspot on the surface of this nanoparticle. And also when you use dimers, as I was saying, if you use 2 dimers, so the main area is in between, which is the even bigger hotspot, this area, and that gives you even better resolution, more confinement, like this one, detection volume reduced by a factor of 6,000, and also more enhancement. Right. So this is going to be like so this I intend to be the last slide of my lecture right now. But what I want to say at this point is, this is just one method that I showed you. So there are plenty of other methods of using nano optics. Let it be surface plasmon. There is also a near field optics method or metamaterials method. You can explore into that. So there's a plenty of light matter interaction going on at nanoscale. So at this point, I'll say, okay, thank you very much. You can look at this slide. You can have questions. You can tell me at this point. So I'll stop now and I'll ask for Asutosh to go ahead and see the questions and everything.
Yeah, thank you for your valuable time. Actually, we are opening the session for the question answer session now. So if you have any question, you raise your hands. I will unmute you. You will receive a request on your screen that host want to unmute you. So you just press OK button and then you will be unmuted and ask your questions. So I can see 2 hands raised. Vijay Gandeer. So I'm unmuting you. You can ask your question. Vijay Gandeer. Are you there, Mr. Vijay Gandeer? I don't think it's there. So if you have if any participant is having any question, so they can write in the chat box also, or they can raise hand. Both options are open.
Yeah, or if you want, I don't know, Asutosh, if there is an option of like if someone wants it later, they can send you an email and you can send it to me and I can reply them back. Let's say up to today, you have today the whole day. If you have some questions, you can write it to me. I can write it back. and I can direct you some reference and stuff like that.
Okay, that we can do.
Yeah,
Yeah.
because I don't know if people are, so I think people are raising hand by mistake as well,
Yeah.
or so yeah, we can take into account as well. Yeah.
Okay. So if any that the participant is having any doubt or any help they want to have from the speaker side, they can write a mail to them. I will say the mail ID.
No. Okay, I said you send your email ID and you get the
Okay, I will
questions,
forward the
collect the
question to you.
questions,
Okay.
and then you can forward it to me,
Okay.
and yeah, then I'll write it back to you so that you can forward it back to them.
Sure. Sure. Sure.
So you are the organizer, so you are the channel.
Okay. Nice.
Yeah.
So you can write on the mail on the institute mail ID, the invitation, the mail you received the invitation from, and we will like to redirect the question to the expert.
Yeah, so
So
just be aware that you have today, the whole day. I'll keep checking in between, because from tomorrow I'll be very busy. I mean, I'm busy right now, but yeah, I can take time out and give questions and take questions and answers as well. Yeah.
sure.
Okay,
Okay.
great.
Now I would like to invite Professor Anushka Sharma to for the word of thanks session. Professor Anushka.
Great.
One second. One second.
So thank you, Dr. Ashutosh. On behalf of New Government Polytechnic Patna Tera, I present a vote of thanks to all those who have contributed to this webinar. So first of all, I would like to thank our resource person, Dr. Deep Punj, for giving his valuable time and delivering such a wonderful session. As he said, you can. This topic has plenty of things to do research in this, so students can take this for their future pursuit of research work. Second, I would like to thank the organizing committee and the technical team for conducting this webinar without any technical glitch. Then I would like to thank the students and faculty members who come up in such a great number and contributed to this webinar. Thank you so much for your cooperation. So with these warm words, I would like to end this session, and I would like to hand over to Dr. Asutosh to conclude this session. Thank you so much.
Thank you, Professor Anushka. So thank you, Dr. Deepun, for your valuable time, and thank you all the participants for your presence. And I'm sure that you have benefited from the session. And later on, if you will need any help in this area, whoever is working in this field, they can contact our institute, and we will redirect your doubt or any help that you need to Dr. Deepun. At this, we would like to end the session, and I would like to thank again Dr. Kunj for your valuable time.
Well, thank you very much, Asutosh and Dr. Anushka as well, to give me this chance, I said, or having me to your webinar state. Great. So yeah, I enjoyed it a lot. And then, as I said, so you can forward the questions to me. It was a lovely session. Yeah, and well, if for example, it can motivate a lot of people in India, because most of the time we don't know, or the students don't know how to move forward in the future. So this might be helpful for their like what they want to do in future, right? So yeah, go ahead. And in future also, if you want to talk to me at some point, you can go to my website. So you can type my name and you can find my detail, and you can email me in order to know more about this topic as well. So I think I'll appreciate that as well. So yeah, thank you very much. Yeah.
Thank you. Hope to see you in India very soon.
Great. Yeah. Well, bye.
Okay. Okay.